Hello, we're going to talk about Hooke's Law. This will be a pretty brief lecture because we've already done a lab on it. So this should be fairly quick for all of you. If you need a moment, you can pause the video and just copy the graph down that I've drawn on the page there. You don't need any numbers, just the axes and such. All right. So we're talking about the force of a spring, and that is force elastic. So that is what Fe stands for, elastic force. So a spring would obey that, also a rubber band or anything that's stretchy would obey that. And this is a different force from ones we've had in the past, because most of the other forces we've had in the past have been constant. So for instance, in any given problem, you might calculate the weight or force of gravity acting on something, and that's equal to mg. And that number doesn't change in that problem as long as you don't change the mass or gravity. You don't change Fg. Same thing with an applied force, like you might pull with 20 newtons on a cart, and that in any given problem, that was a constant force. Well, this force varies as you move. As you stretch the spring out or as you compress it, the force gets bigger. So that's what's different about this force. It varies over distance. Now, as you learn in the lab, there's an equation for this graph, and that's pretty simple. It's a line, and it's Fe equals K times X. And K, if you look over at the graph here, K is simply the slope of the graph. Okay, and you guys learned about that in the lab too. Okay, the units for K, well, when you do slope, you're doing rise over run. So what are our units? Well, our rise units are newtons and our run units are meters. So your units for your slope are newtons per meter. And that is the stiffness of the spring, how hard it is to compress or stretch. All springs are different. They all have different values for K. It depends on the spring. A little watch spring would have a really small value for K, and like a car spring or a garage door spring would have a big value for K. Now, technically, and if you look this up on the internet, technically there should be a negative here, okay? Don't worry about that and don't worry about putting it in. All that negative means is the direction. If you pull a spring to the right, the spring pulls back to the left. That's the negative. But in all of our calculations we're going to do, you don't need to worry about that. We're only looking at the size of the force. So you'll notice on your formula list that I don't have the negative there. It's just F equals Kx, okay? And by the way, as a reminder, X is how far you stretch the spring from its equilibrium position. Its equilibrium position is simply where it wants to be if there's nothing pulling or pushing on it. Okay. Now, I will do a couple examples with this. They're fairly brief. Example one, okay. Let's say you have a spring and you stretch it 30 centimeters. So that would be X. And we'll put 30 centimeters there. And let's say in order to do that, it takes a force of 60 newtons. Okay. What's the spring constant? So I'm asking what's K? Okay. So our equation is F equals Kx, or Fe equals Kx. Since we're solving for K, I'm going to get that by itself. So K is Fe over X. Now, the one thing to be careful of here is your force must be in newtons and your stretch must be in meters. Well, I gave you 30 centimeters. How many meters is that? Well, that's 0.3. So this ends up being 60 newtons over 0.3 meters, and that would be 200 newtons per meter. So that would be your spring constant for that spring. Another quick example, we'll call this example 2. Okay. Let's say I give you a spring with a constant of 200 newtons per meter, so the same spring. So I'm giving you K, so that would be 200 newtons per meter. And let's say I want to stretch it now, instead of 30 centimeters, I want to stretch it 40 centimeters. So I'm giving you X. Okay, how much force is that going to take? All right. Well, again, we're using the same equation, Fe equals Kx. And this time I want F, and so I've already solved for it. So I take K, which is 200. And again, you got to write X in meters, which is 0.4. And you're going to get 80 newtons. Okay. So that would be how much force you got to apply to stretch the spring 40 centimeters. The last example is a little more involved. Okay. Let's say you got a spring very much like your lab. Okay. Let's say I got a spring hanging from the ceiling or from a hook or something, and I hang a block from it. Okay. And the spring, that's the before picture, and here's the after picture. Okay. All right. And let's say the block is 200 grams. Okay. And let's say the spring stretched. Oop, and let me try to draw that a little better. Let's say the spring stretched 12 centimeters. All right. What's the spring constant for your spring? Okay. Well, again, we're going to use Fe equals Kx. Okay. And I want to solve for K. So that equals Fe over X. Now I know X is 12 centimeters, which is 0.12 meters, but I don't know Fe just yet. But what I do know is when I hung this block from the spring, it made it stretch 12 centimeters. What force is pulling down the block? Well, if I draw an FBD here, okay, the force of gravity is pulling down on the block. When the block gets to this position, it stops moving. That means whatever the upward force is has got to equal the force of gravity, and that's your spring, which is your elastic force. So when the block gets to this position, these two forces are equal. So we can figure out what Fe has to be. Fe is going to equal force of gravity, which is going to be mg, which is going to be, now, you got to be careful here. It's 200 grams is your mass. How many kilograms is that? Well, you got to divide by 1,000, and it's 0.2. So your mass is 0.2, and then gravity is 9.8, and you get a force of 1.96 newtons, okay? That is the force that you plug in there, okay? So your K value will be 1.96 newtons over 12 centimeters, which is, again, how many meters? 0.12, okay? And that's your K value. If you divide those in a calculator, I got 16.3 repeating, and it's newtons per meter. That's the units for K, okay? Now, I could ask you questions like, hey, if you wanted to stretch that spring 1 meter, how much force would it take? Well, it'd be Kx, which would be 16.3 times 1 meter would be 16.3. Now, I could ask you, hey, if I wanted to stretch that spring 2 meters, how much force would it take? Well, now you take 16.3 times 2, and you would get 32.6 repeating, and so on. Okay, so that's what K is telling you how hard it is to stretch the spring. Okay. All right, I hope those examples were helpful. Good luck on the sheet.